Hey, so this is Joseph, and this is the first part of the fourth chapter of Stewart's calculus, and we're going to be talking about the definition of the integral. So the integral is basically the mathematical answer to this question, the area problem, and the problem goes as such, pretty simple one. How do we find the area under a curve? So that could be desirable for many reasons that we'll see later once we actually define an integral, but it's a kind of awkward problem to solve because curves, the curve changes, they're curvy, it's difficult to find the area under. So we're going to go try to do that right now. And first off, we're going to get a really good approximation, or not a really good, but an approximation for that area. So first, we're going to try to approximate the area under the curve y equals x squared, pretty familiar parabola, between 0 and 1. So we're going to write that out like this. The area between 0 and 1 on the xy. And that's one thing that you always have to specify when you're finding areas under curves, is the interval under which you're finding it, because curves go on infinitely. And so the first way that we can think of solving this is by drawing little rectangles into the curves. We can approximate with rectangles. Now there are two things that we have to bear in mind when we're using this kind of rectangle approximation. Actually, it's called a Riemann sum when we use rectangles like this. Like that. And we have to pay attention to, well, where is the corner of the rectangle going to be resting? So we could make the left corner of the rectangle rest on the curve, or we could make the right corner of the rectangle rest on the curve, or we could even let the midpoint or some other point of the rectangle rest on the curve. So these are the three most common types of Riemann sums, and the names are pretty simple. We've got left, if it's the left corner on the curve. We've got right, hand Riemann sum, if the corners on the right corners on the curve, and we've got a midpoint. Midpoint if it's the midpoint on the curve. So I'm going to show you a couple of examples of how we solve that. And the second thing you have to pay attention to when you do this is how many rectangles you're going to be using on this interval to approximate that area. So here we go. Let's approximate using first a left-hand Riemann sum, the area between 0 and 1, and we are going to use 4 rectangles to do that. So, and remember this is left hand. So if there were to be a rectangle here, the corner would be resting at, at 0, at y equals 0, so we don't draw a rectangle there. Second rectangle, go up and over, because we're using 4, so the intervals are going to be a quarter long. Draw them out like this, and boom. So the area between 0 and 1, and so each of these are going to be a quarter. We've got 1/4 times, and then right there that's at a fourth, and then a fourth squared is going to be 1/16 plus a fourth times, and then that's at a half right there, that point on the curve, so that's f of a half. That's 1/4 as well, plus a fourth is the base length, and it's all the base length, times f of 3/4 right here, which is going to be 9/16, and then just remember that little quarter. And so that is the Riemann sum approximation for this area using 4 rectangles. And once we get that all out, that is going to be 7/32. And note that when we use the left-hand approximation with this curve, we're underestimating it because there's all this blank space right there. Now, let's try the right-hand approximation. So, same deal, a 0 to 1, we're going to use 4 rectangles, but this is going to be right. So, we draw the rectangles like this. The second one, third, and final. So again, so look at this, we're overestimating now, but we have got a from 0 to 1 is about And so the height here is f of a quarter, and the base length here is all still a quarter. Actually, I'm just going to automatically factor that out now that you kind of see how this works. And so that is a quarter right there, that height, plus, and then that's a half squared, or, oh sorry, that's a quarter squared, that's 1/16. That height there is a half squared, so that's a fourth. My mistake. That's 3/4 squared, the height, and that's going to be 9/16, and that's 1 squared, so that's going to be 1. And remember, when we distribute that fourth, you're going to get the areas of all these rectangles, because that's just the formula for the area of a rectangle. And all that is equal to 30 seconds. And graphically, this makes sense that this is bigger than the previous answer, because we're overestimating this area here. Now that we have an approximation like this, we can be able to find an exact way of solving for the area under the curve, not just an approximation. So, in order to do that, let's figure out a formula that will be able to tell us, or at least describe generally, how Riemann sums work. So, I'm going to draw that out here again. So, we have the base length here, and that base length is all constant. And we can call that change of x, and that change of x is going to be the same for each length. And then the heights of each of these rectangles, that's what varies. Well, actually, the height is what varies, and the number of rectangles used to approximate each area varies. But the height can be described as f, whatever the function is. In this case, it's x squared. F of x sub some number. And so, like, for example, a quarter here, that would be x sub 1. Half would be x sub 2. And that where those points are, points of x, varies as a function of how many rectangles there are. But the point is that interval is always the same. And we can use this notation, we can have a little asterisk up here to tell us that that's a sample point. And that sample point, we can kind of define how spaced out they are, and it's just to be understood that that spacing is going to be constant based on how many subintervals we use, how many rectangles, and what the change of x is. So we can actually kind of explicitly describe this approximate area using the Riemann sum. So A is about equal to, and then use summation notation, I equals, and then that's going to equal the beginning of the interval. In this case it's 0, but generally that can be described as A, between A and N. And so that n right there, that is the number of subintervals, or number of rectangles you're going to be using in your approximation. And so you sum up all the little areas, and so the little areas are going to be height times base. So f of f of x sub I starred times that constant change in x. And that is the general formula for Riemann sums. Now, in order to get an exact value for the area under the curve, it seems like we could make these rectangles super skinny so that they basically just resemble lines. And it looks like, and intuitively, it feels like we should be able to figure out the area that way. And what we would need to do then is make this value, you've got to make this value right here, we've got to make that approach 0. So now that we have kind of a graphical understanding, let's go back to the white screen and work this out. So initially you may think, in order to make this change in x approach 0, what we would need to do is have some sort of limit notation where the change of x approaches 0. And that is potentially like a possible way you could go about it. I don't know, I haven't tried, maybe it's not possible. However, remember that this expression right here assumes that this change in x is constant, and for all the summation it doesn't change, and this assumes that each of these sample values of x is proportional, is going to be even with respect to this change of x, and with respect to the number of subintervals you're using. So it seems like the subintervals are the thing. This n value is really what plays the largest part in determining these two other factors. These two other factors are largely dependent on that subinterval. For example, from 0 to 1, if that n turns into a 5 or a 6 or a 7, then we have a means of figuring out what the change in x is going to be and what all the sample values are going to be. So actually what we're going to do is, since also this is an area between two values, we're going to call them a and b, that doesn't change. The only thing that's really changing, or that's significant that's changing, is this n value. And so if the bigger this n value gets, the smaller this change in x becomes, and the closer together these sample points become. So what we really need to do is make this n approach infinity for a closed interval a and b. So we can define the integral, and the integral is going to be the expression for the area under this curve, by the way, if you haven't kind of caught on to that. So the integral, we say the integral between a and b, which is equal to the area between a and b, and this sign here is called an integrand, of a certain function x with respect to x, because you can also integrate with respect to y, which we'll do later on in this chapter. This integral, which is the area of that function with respect to x, is equal to the limit as n approaches infinity of this summation right up there. So the sum of I equals a and change in x. So that is the definition of the integral, and we can actually solve these limits for problems, but we never do. You will use the definition of the derivative on the AP test. You will not use this definition of the integral really on the AP test. And we're going to show you some more ways to define an integral with respect to derivatives that make them a lot easier to solve than using this definition. This definition is really just a conceptual thing to kind of get you to understand how integrals work and why they can tell us what the area under the curve is. So there you go, that's the video for today. Stay tuned for the rest of chapter 4. A lot more in integrals, definitely super interesting. Fundamental theorem of calculus is coming up in this chapter. As the name goes, it's pretty fundamental, so yeah, stay tuned.